See something, some red mark.
No, I cannot see the pointer. Actually, yesterday also this was the same, but yeah.
No, this pointer might be difficult, but the pointer, the mouse pointer, I can see. Mouse pointer, you can see.
Can you move the mouse pointer?
Can you check? No, not that one.
I am not connecting by my laptop, so.
This one, can you see that?
Oh, yeah. This you
Yeah,
can.
yeah.
Yes.
The
The hand.
hand.
Yeah. Yeah. The hand. Yes. Thanks.
Can you see this one? Can you see this one?
No, I cannot see. I don't know who else is there. Shango is also there. I cannot see it at least.
Yeah.
Me neither.
So mouse is fine. You can use. Yeah, you can do if you want to force something, just slowly with the lowering the.
Maybe you can keep that mouse there.
Exactly. And to change the slides, you can use the remote. Yeah.
We are happy to have Sandeep Kumar Acharya from Indian Institute of Statistics from Bangalore. So he will be talking about props of standard model of cosmology.
Thanks for the introduction. So I will talk about probes of standard model of cosmology. So this is the brief history of the universe. So the universe started with a brief period of accelerated expansion called inflation. So the universe was hot, dense, and ionized. So therefore, the photons and electrons are coupled. So the universe was opaque. But as the universe expands, the temperature goes down. So at around 400,000 years, this universe was cold enough that the electron and protons recombine and form neutral hydrogen. And therefore, afterwards, the primordial photons started to escape. And the neutral hydrogen, they started to collapse under their own gravity. And as time progresses, they form the galaxies that we see in the universe. As the time progressed, these smaller galaxies started to form bigger and bigger structure and form the matter distribution that we see today. So observationally, the universe is given by a spatially flat metric. So and the expansion is captured by this scale factor called A, and the equation of motion of universe by solving the general relativity equation, you get this kind of equation. So this is the evolution of a scale factor, which is related to rho, which is the energy density of the universe. So due to the expansion of the universe, so the wavelength of light gets stretched. So if a galaxy is emitting light at a wavelength of lambda at a time t, we see a different observed wavelength, which is related by this equation. And we define a quantity called redshift, which is the fractional change in the observed wavelength, which is related to the scale factor. So therefore, for the purpose of this talk, the basically redshift, and redshift is basically a proxy of cosmic time. So this from this equation, redshift and the cosmic time is basically there is a one-to-one mapping.
When do you write this? When you write this equation for your expanding universe, when is the starting time? Or when can you write this equation as a valid description of the world?
So
you showed different stages in the early universe. So when you write this equation, what is the starting point?
T0 we don't know, so basically we are going backward in time.
But in your standard model of cosmology that you showed, so
yeah,
what can
so
be the possible region from where you start your this equation to be valid, you expect it to be valid?
So for the observed universe, like say a few thousand of redshift, so this seems to be valid. But as you go to very high redshift, it is not observable. So we don't know if it is valid or not. So for the available data, cosmological observation seems to be
But in the inflationary phases, you cannot describe this universe in such a simple term.
No, you
That's-
can actually, if it is moving as an isotropic and if you think that
No, you don't know that.
GR, okay, if GR is valid, then no modifier, then you can write. These two are the assumptions that, as long as it is right.
So we define the, so in the literature, we are interested in this quantity of the Hubble parameter, which is the rate of change of the scale factor. And the value of this Hubble parameter at today or redshift 0 is called Hubble constant. It is a fundamental interest because this relates to the age of the universe by this equation. So to measure this Hubble constant, you can use some astrophysical observables. So I will discuss one such astrophysical observables which are called fast radio bursts. So basically what we do is basically we measure the distance to these observables and the redshift. So in which galaxy these are located. And basically Hubble parameter is basically the transformation factor between the distance and the redshift.
And I would like to ask, what is the specific definition of the age of the universe? How do you define?
So this TH is basically dominated by the time, late time. So when you start somewhere period T0, whatever that
This
is,
is the time from where you see the structure formation.
yeah, basically dominated by late universe. So it doesn't matter where, like your T0 definition doesn't come into it. It is mostly dominated by loads.
So, if you look at this scale, age, what is that typically get?
13.7 billion is that episode.
How do you find the distance?
So we measure the flux. Flux is luminosity over distance square. So we need some technical to determine luminosity. So I will have slides.
Is it standard?
So for this fast radio burst, I can locate this into a given galaxy. So we know the redshift. And we measure something called dispersion measure, which is a measure of distance to those fast radio.
What he's asking is the fast radio was a standard candles kind of. Standard.
I mean, is it universal in total? So for supernova, it seems like within our understanding, at least empirically, the luminosity seems to be standardizable. So because this is supernova within different galaxy types, so one has to take into account some biases and some, but we think that we understand that, but that can be wrong. So it is standardizable candidate, not the standard. So we have a standard lambda setting model of cosmology. So this pie chart shows the energy budget of the universe today. So it is dominated by this component called dark energy or lambda, which is about 7 times. It is lacking, so they cannot see.
Actually, maybe you should also sit down because that angle is difficult for me. You can
Yeah,
sit down
yeah,
and
yeah.
you're bending over so much, you can go to sleep. Just sit and back then. And you can throw that away and use your mouse even to change the page and everything is happy.
So the dominant component is the dark energy or lambda, which is about 70%. And the rest of the component is not showing in the slide, is matter. And this has two components. So the sky, the blue one is basically the cold dark, what is called cold dark matter, which is about 26%. And the green one is the baryon, which is mostly hydrogen, but about 10% of it is helium. So the cold basically refers to non-relativistic particles. So basically, our understanding is that the dark matter collapses under their own gravity to form potential wave. And the baryons, once they decouple from the CMB of the photons, they fall into those potential wave to form galaxies, etc. So the distribution of galaxies is somewhat of a proxy of particle nature of dark matter. So at least on large length scale, like more than megaparsec length scale, we think that from the galaxy distribution, we think that dark matters are non-relativistic. But at small scale, it can change. So basically, we can use these cosmological observables to basically constant the particle nature of dark matter, and I will discuss one such example in this talk. So this plot shows the evolution of energy density of the universe as a function of redshift. So in the previous slide, I showed this energy density at redshift of 0. So it is dominated by dark energy and the matter. But the matter starts to get become dominant component at redshift of 0.3. And that the radiation is not important at low redshift, but as you go to high redshift, it becomes the dominant at redshift of about 3000. So this 1 plus Z, so the Q is basically due to dilution of number density, and the radiation density has one extra component of redshift because of the stretching of the wave. So in the standard model, the radiation energy density is the sum of what is called cosmic microwave background photons and neutrinos. So we parameterize the total radiation density in terms of rho CMB by this way. So N effective is whatever radiation density except the CMB photons. And so in standard model, N effective is 3, which is 3 flavors of neutrinos. So this
Here you are taking relativistic.
this is the radiation. So
So there is exactly not free because some details about is that important for your talk on why
no,
it's not. So you don't have that formula anywhere. Okay.
so these two plots shows the thermal history of the universe. So in the left, I have the temperature. So there is a matter temperature and the CMB temperature as a function of redshift. In the right, I have the ionization history XE, which is the ratio of electron to hydrogen, combining neutral and ionized hydrogen. So at redshift of redshift higher than 1000, the universe was very hot. So the electrons were free. So once the universe cools down, the electron and proton recombine. So there's the density of free electrons goes down. But as the universe keeps on expanding, so because the number density is so small, the electrons find it difficult to combine with protons. So therefore, this curve does not keep going down, but it starts to flatten out. This is called a freeze-out fraction. Freeze-out.
Sorry, what is the left plot?
The temperature of the
Okay.
So at around redshift of 20 or 30, the matter starts to form, and this matter emit ionizing photons. So once again, these neutral hydrogen can be ionized by this radiation. Therefore, this
The difference between recombination and matter formation. Of the,
so there is no matter. There is a free electron and proton, but here you have like a neutral gas.
when you call recombination, what to precise?
Electron and proton forming neutral hydrogen.
To hydrogen. But then why is freeze out necessary to?
So this is a. So if you compute this one, so it will come out freeze-out because this does not go down.
Because typically what happens in this type of thing happens in heavy ion conditions. You have to cool it down sufficiently so that the freeze out happens. So what is your definition of freeze out?
If you solve this equation, taking into account the expansion of the universe, so this is naturally come out. So I'm not
Freeze out, definition of freeze out.
Is it kinetic freeze out? Like, what is the freeze out? Chemical freeze out? Or what? How do you define it? Like in terms of elastic?
Hydrogen slows down.
the
No, the
recombination
elastic
process.
elastic collisions, which one?
Oh, I think the flattening of the curve is
Flattening of
what
the
he calls freeze out.
Okay, so it is not technically.
But your number of hydrogen, neutral hydrogen atoms, their number also flattens. What is the density?
Yeah, and yes, because this is N is 10 to the minus 3, so practically everything is neutral. This is N of 10 to the minus 3.
And this is happening because the chemical composition is not changing anymore.
No, because the universe is so dilute, the electron cannot find a proton to recombine.
So whatever has formed a neutral hydrogen, they form, or otherwise everything others are free.
But it is like negligible. 10 to the minus.
Photon dilution is the phase out.
Not photon, this electron and proton cannot
No,
recombine.
that is because photon is not scattering.
The photon has decoupled at redshift of 1000.
Yeah, so that's why I was thinking that we were referring to this, that is why we usually refer to this as the result, but when you said without it, I was thinking that you are defining an epoch, particular epoch when it becomes
No,
epoch.
it's just non-technical way, just flatten out.
Okay. Okay, thanks.
Why it is rising it again?
So yeah, at rate set of 20 or 30, the structures galaxies form and they emit ionizing photons. So these ionizing photons can then start to ionize nuclear hydrogen. That's why this curve starts to go up. And from cosmological observation, we think that at around rate set of 5 or 6, the universe gets completely ionized. So in the left plot,
Galaxies are ionizing themselves.
they emit photons. Some of the photons can escape their nucleus around. Photons can
What happens to the, I mean,
No, you're saying galaxy, but you mean star, right?
yeah, even stars. Yeah, I mean, if we are not going back to the same situation as if there is and soup of electron and protons.
Yes.
What happened to the galaxies then? They met out.
Some of the most of the photons are like this, we don't escape, but some of the photons escape, but the number of variance is so less in the universe that small number of photons is enough to basically have this all of the hydrogen.
So sorry, the question might be more like, isn't it true that most of the hydrogen is in intergalactic space?
Yes.
And then there might be bound hydrogen in galaxies or not, but they don't count much, right? Is that the thing?
Yeah.
Then it's correct.
All the hydrogen is intergalactic. And also both the numerator and denominator are changing. So that is why his value goes to 1, right? He's only talking about the free and bound hydrogen, or not what is inside the galaxy or stuff.
Area surrounding the galaxy, then all those are always.
Right near the galaxy. But there's a lot of starlight, so they would be.
It depends on what redshift, but this actually is the overall picture type.
But anyway, the area surrounding galaxies don't count much for it.
It's the background, like not the part of it. So
No, but that's a very low volume, so they don't count much in this total line.
So in the left hand panel, I'm showing the evolution of temperature. So at very high rate shift, the Compton scattering between the electron and photons is very effective. So that's why the temperature is basically the same. But once they decouple, the electrons temperatures goes down faster. Then once the structure forms, so basically you see this same feature here. You see the same temperature is basically rising.
Sorry, why is it that matter temperature goes down faster?
Because it has 3 degrees of freedom, photon has 2 degrees of freedom. So for same energy, the temperature is due to incompatibility. So in this talk, I will talk about 4 cosmological probes. So one is distortion in CMB frequency spectrum. Second one is CMB spatial fluctuation, or what is called CMB anisotropy. Then 21 centimeter distortion, and then faster fluctuation. So the cosmic background is basically the relic radiation, photon radiation that fills the universe. It is extremely homogeneous and isotropic. So before recombination, they are coupled to the electrons. So once recombination happens, they basically decouple. So basically the CMB map is basically a snapshot of the universe at a redshift of 1000. So in this plot, I'm showing basically the observed frequency spectrum of the CMB. So there are error bars, but the width of the error bar is basically less than the thickness of this line. And one can fit this data with a Planck spectrum with temperature around 2.7 Kelvin. And if you plot that in terms of frequency, so the peak of the Planck spectrum will be around 150 gigahertz. And we define distortion is the difference between the actual CMB spectrum and this best fit Planck spectrum. And with this data, the coordinate constant on fractional distortion is less than 10 to the minus.
So this delta I nu is a function of frequency?
Yes. Okay. So there can be different sources of the spectral distortion. So basically for the Planck spectrum or thermal spectrum is just a function of one parameter, which is the temperature. And the
lot of spectral distortion, not the 10⁻⁴ that you said. It's like we have just plotted the blank spectrum, best way to subtract that out. How does it look that observation you have in delta I mean the observation as a function of okay.
Yeah, so there can be different sources of distortion. So I'm talking in this slide. I'm talking about pre-recombination universe or the distortion formed before it's at 1000. So basically, the Planck spectrum, thermal spectrum is a function of one parameter, which is temperature, and the number or energy is fixed by that temperature. So if you basically create a imbalance between number or energy or both, you can create some distortion. So basically, one can have a distortion from adiabatic cooling. Like from previous plots, you see that the electron temperature goes down faster with respect to redshift. So therefore, CMB photons spend some of its energy to keep the variance at same temperature. But the scattering process, which is the Compton scattering, is a photon number conserving process. So the photon number does not change, but the energy changes. That's why there is a distortion. And in the second case, there is something called recombination distortion. So when the recombination happens, so you
Sorry, why does the photon number change?
It's Compton scattering. So Compton scattering number. So around recombination, you can have these lines from recombination between electron and proton. So these are basically different hydrogen lines, and these are very small. So these are not yet detected. So, but people are planning to detect it in future experiments.
Sorry, what is the reason for vegan?
These are all so electron can recombine.
Sorry, this is the Compton scattering you're talking about?
No, that's the. It was for this number one. So this is the recombination distortion. So electron can recombine to any of the higher levels of hydrogen. So that's why it is different.
So each peak corresponds to a different line.
And also there are some features from William also.
But how about this Compton scattering distortion? Is that also in this plot?
No, this is not Compton scattering. So the for adiabatic cooling, the Compton scattering.
So it won't show up in this plot. Is that what you're saying? The effect of Compton scattering.
No, so whatever C will be like a mixture of all these. So you have to distinguish. But like adiabatic cooling and recombination distortion. But this adiabatic cooling is coming from distortion coming from adiabatic Compton scattering.
Which is there in the plot.
No, this is a different. This is for this number two.
Yeah, so that won't show up in delta I nu. Okay, because it will be a smooth distortion. Which okay.
So from so the delta I nu will have four components from your, if I understand correctly.
Yeah,
Delta I nu one for the components.
So
two
this
for the
so this number one and number two is predicted from standard model of cosmic energy. But this electromagnetic energy, so these are basically can be dark matter decay or annihilation or primary black hole evaporation. So we are not sure.
all of them has to be added.
Yeah, I will talk about this electromagnetic distortion coming from electromagnetic induction. So these can come from beyond standard model theory like dark matter decay, annihilation, or evaporating parallel black holes.
And when you talk about this photon number, so how do you define it within the black body? Because black body, there can be creation and annihilation.
It is in equilibrium to begin. So you can only scale. So once you create distortion, then you have to take into account the interaction.
Has this two been observed already?
No, these two are very low, like 10 to the
What is the
minus.
present limit? I mean, they're 10 to the minus 8 to 10 to the minus 9. How? What is the sensitivity now?
10 to the minus 4. That is
10 to the minus 4. Also, the average.
So one can also have this distortion signature at post-recombination universe. So you have these clusters of galaxies. So they can host thermal electrons up to keV temperature. The typical redshift at around redshift of 1, the CMB temperature is of the order millielectron volt. So you have electrons like a screen of keV in keV energy, and the photons are basically passing through this galaxy cluster. So they will get boosted by Compton scattering. So in this plot, I am basically showing the observation of a one galaxy cluster across different frequency. So in the blue is basically deficit of photons because of this boosting, some of the photons from low frequency or lower energy have been scattered to higher energy. So for these frequencies, there is a deficit of photons, and at higher frequency you see increasing photons. So I will describe how this is created in better detail in next slides.
So the right,
You are calling it thermal electron. All the energies are much lesser than the mass, the temperature.
This is kinetic energy.
Yeah, it's less than the mass. So how does the distribution look like?
Maxwell equation. This is like an assumption. You can also have non-thermal electrons like power law kind of relativistic. But this is like a starting point of most of the cosmology.
No, if it is relativistic, then it should look like a Fermi sea, right?
It may be like a subdominant component of total electrons. Like relativistic component can be really small component of total electrons. But from observation, you find that the thermal electrons is the dominant.
the right plot, the red thing, is that also Compton scattering or is that direct emission of photons by the electron?
This is just a map. So we have the Compton scattering, but also infrared radiation.
So which is the dominant one?
Dust at 545 gigahertz, this dust component is the dominant one.
Meaning direct emission of photons from the electron.
Yeah.
That's the dominant. But in 353, they are
It's like but you have to use all the frequency map to distinguish one two.
okay.
That's right.
And what is this? What is this experimental signature that tells you that the
There is an analytical formula that so basically if I give you the distortion at like 70 gigahertz, you can predict what should be at 143.
this is assumed that like a Maxwell movement gas of electrons.
Yes.
That's the only other.
Yes. And the scattering is non-relativistic. Counter scattering is just functions. So don't take into account relativistic curves.
This frequency distribution, you just get it from Maxwell. You
So
have
this is the like a
probability
detector.
curve.
These frequencies are for the detectors of the Planck experiment.
Why shouldn't there some red thing in that 70?
Side.
So maybe some
So
what does this blue and red actually is increasing the
Yeah,
distortion, or it is makes the photon energy is getting distributed to the electron?
so some of the photons are basically missing. So this blue says that there is a deficit of photons compared to the Planck spectrum. And the red one is basically increasing number of photons.
Okay, the medium is actually supplying some of the photons in that where they
I mean, the photons number doesn't change. The electrons basically boost the semi photons from low frequency to high frequency.
Okay.
So there is no creation of distortion.
just energy is getting
The CMB map is not completely isotropic, so this has some special anisotropy of the order of 10 to the -4. So in the right hand side plot, I'm plotting the power spectrum or the Fourier transform of this map as a function of L, which is called the angular multipole, and it is roughly given by pi over theta, where theta is angle on the sky. So smaller L corresponds to larger theta or larger physical length scale, and higher L corresponds to smaller length scale. And these oscillations are what is called baryon acoustic oscillations. So basically, in the high redshift universe, the photons and electrons are coupled, tightly coupled. So they behave like a fluid. So if you have like perturbation, it sets up sound waves. And so these are this kind of oscillations. And at lower length scales, so basically you have like a hotspot and cold spot, but the photons can diffuse through hot to cold medium. So basically they average out all the perturbation. So this perturbation basically damps out at high L. And these are the data points, and in the solid line you see the 6-parameter cosmological models. So that is our standard cosmological model.
and why are these error bars large? Small
because you have one map, one CFD map. So this L, small L, basically means higher theta. So if you divide sky into very large patch, in one sky there will be very few patch because due to statistical limitation. So there is this
Costly value.
Are there any other things reasons or is it just because of your limited data?
limitation means
The cosmic variance that you explained. There's statistical data to sample. But are there any other physical reasons happening in large distance things? Or it is just only history?
I mean, you cannot constrain any. Whatever physics happen, you have to go to some other data like other external cosmological data to constrain whatever.
And the small distance case, we're telling something about hotspots and things.
So basically, you have so photons at high temperature and low temperature. That is basically the anisotropy, but they can mix together. And that basically averages out whatever anisotropy. That's why this happens.
Why is there a mixture of this?
Because photons cannot cloud, so they are relativistic. So that becomes important in low length. So one can use this CMB anisotropy observation to constrain different kind of physics. So I am showing a few cases which are of recent interest in recent literature. So one can constrain expansion of history before recombinement. So this early, there is some example called early dark energy. You can constrain particle physics process like Newton, sample interaction, dark radiation, etc. And you can find extensive test of models in this paper. For post-recombination physics, so CMB on its own is not powerful enough to constrain it. It can constrain the combination of parameters, but it cannot break some degeneracy. So one has to use external data such as supernova or capacitor circuits to break this degeneration.
And when it is pre-recombination physics, it is up to the preheating stage? Or?
Up to redshift of 1000. So recombination is the test.
But how far do you go early? Is preheating stage?
Not sure about preheating, but
Preheating is the particle production after the inflation stage. Sorry.
potentially you can, but next question.
That may be a little bit too early because electron production may sometimes be thermalized. I think all the formalism that you have can only explain thermal systems.
So my first topic of this talk will be concerning decayed dark matter to electromagnetic particle. So I will discuss this one specific model for decaying dark matter, but the idea is generally applicable to dark matter annihilation of binary black holes, evaporating black holes, etc. So I parameterize. So basically, yeah. So the dark matter decay basically injects some electromagnetic or photon pair. So for simplicity, I assume that it's monochromatic. So this energy injection rate is parameterized in this form. So Fx is the fraction of decaying dark matter compared to total dark matter, and tau is basically my lifetime.
Sorry, tau is what? Sorry.
Lifetime of the particle.
Why exactly is parameterization?
It's a simple.
Monochromatic bands. Following this. Oh, because of the radioactive band.
So E then means the distribution of energy.
This is over time oriented.
No. E. What is it? E is a distribution of energy. Distribution function. What is it?
The function, so energy as a function of time oriented. So you do not inject energy at one time, but over a period of time. So I need a function how to inject energy. Okay. So the classic calculation of this CMB spectral distortion goes back like 50 years. So this has some assumptions.
The network tower.
I is going to be my tab. So what this calculation assumes that whatever electromagnetic energy that you inject, it basically hit the background electrons. So basically the electrons are hotter compared to single photons. So they can actually upscatter the single photons. So basically that we'll see that in the top panel. So the red one is the Planck spectrum, and the blue one is the scattered single photons by these hot electrons. In the bottom panel, I'm showing the distortion or the difference between two. So you see that there is a deficit of photons at lower frequency, and these photons are basically upscattered to higher frequency. And this minima is at 150 gigahertz, which is the peak of the single frequency distribution. So that's where the most of the single photons are. And the maxima is given by the kinematics of the scattering process, which is in this case non-relativistic Compton scattering or Thomson scattering. And the differential cross section of Thomson scattering is just a number, so it does not depend upon the energy of the injected particles. So that's why this is called a universal wide distortion profile. So we only care about the total amount of energy that we inject, but we cannot distinguish between the spectrum of the energy of the injected particles.
Sorry, what is the blue and what is the red?
So the red one is the Planck spectrum, the blue one is the scattered semi-photons.
So what is the injected energy? This is blue is after injecting.
Yeah. So the electron is hotter, so they can upscatter the single photons.
So what is the injected? Is it a single?
From like dark matter decay to electromagnetic
So
particles.
what the energy is that injected?
So I'll come to that. So that will
For
be
making this plot. This is for some one energy injected. That is the blue.
yeah. So the point is basically it does not matter what energy.
So it's,
That's why it is a universal.
but then what does it depend on? The number of photons injected,
The total energy that will be.
number of photons.
But for a more general calculation, you have to basically solve this electromagnetic cascade. So basically you have a high energy electron, so it can scatter with semi photons. So you have a slightly lesser energy electron and a boosted photons. And these photons and electrons can again produce the particles. And at last you have a distribution of photons. But these photons, the spectrum need not be thermal. So basically the spectrum of this single photon is given by these kinematics of different relativistic process. So therefore we expect that the CMB spectral distortion say will be a function of your original energy of the electrons.
Sorry, and so this time scale for this this is in some sense a thermalization.
Yes.
So that if you go to the previous one, the blue thing will go back at some point to the red one. Then what is the time scale? I mean, that
So we like 10 to the power 6. So if you inject any energy, vapor is 10 to the 6, everything will come in this.
by now.
But because it is expanding, the
If it was injected after 10 to the 6, you will be able to see a distortion in what you're seeing.
But that also should be in a tau, right? So you're injecting energy over function of time. The tau is also another scale is important.
yeah, tau will be related.
So do you know what 10 to the 6, what energy scale it corresponds to?
It will be related. So let's say 1000 is
So around 100 EV. 100 EV, right? Okay.
So in this calculation, so basically I inject energy at a given redshift, say redshift of 20,000, and then I evolve the distorted spectrum up to present day. So you see that the semi-spectral distortion self is a function of original electron energy that you injected.
But you said that energy will be injected over a year.
This is just a 1 year. So as you basically increase the electron energy, so in one scattering, the electron can give a larger fraction of energy to the CMB photons. So that's why the peak of this distribution shifts to higher and higher frequencies. And
Sorry, what is why?
is like an amplitude of this amplitude of this parameter is the amplitude by factor of 1.
It has some units of K.
No, the Y is like a reference case, which is this gray one.
Okay.
And all these lines basically denoted by what is the energy of the electron that I inject.
Yes.
There is no unit, it's just
Okay. So the same number is injected on.
yes, same energy. It's the energy, so that's why this amplitude actually goes down because more and more number of protons are at high frequency, and the total energy is given by the area under this curve. That's why this amplitude actually goes down. And the same energy that we inject basically can change the recombination history. So this energetic photons can ionize neutral hydrogen. So this increasing effects means more number of energetic photons are added. So that's why this squeeze out fraction is flattening out is basically increasing. So there are more number of electrons.
When we started your original model, so there can put some parameters, some limit you should get recovered the plot that we showed in the previous.
That's how we are constraining this model. So that's how we constraining the tau.
So what means, what is the limit of tau when that your previous plots actually can be described by your
Yeah, the total constant will come.
but ideally I would assume that if your tau is very large, then you should go to this fixed energy. Is it true?
So large tau cannot be constrained by C. So I'll explain why.
What is the effects here?
The fraction of decaying dark matter compared to total dark matter or the amount of emitted.
So that very small component is decay 10 to the minus 8 or something.
Yeah, so as you increase effects because more you are injecting more, so this fraction goes up.
But it makes a dramatic difference for the ionization fraction.
Yes. So because of more number of electrons, so the CMB photons can scatter more number of times with these electrons. So that will actually affect this CMB anisotropy power spectrum. So for the larger effects case, you see some damping. So basically, this scattering basically make the universe more homogeneous. So that is the difference between this black curve, which is like a standard one, and the red one, which is one of the extreme cases. And this plot shows basically the summary of the constant that we obtain for this dark matter decay with the CMB spectral distortion and anisotropy data. So this magenta band shows constant coming from CMB anisotropy. The band is because I am varying the electron and photon energy between KeV to GeV. So the strongest constant is coming around 10 to the 13 second, which roughly corresponds to redshift of 1000. So that is the epoch of recombination. That's why the CMB anisotropy is very sensitive to energy injection around that epoch. And as you go to lower light times, so the constant power goes down because the universe is anyway ionized. So adding any particle does not make any difference. And as at a longer lifetime, you are injecting particles at very low redshift. And at those redshift, the universe is very dilute. Therefore, these energetic particles basically free stream. They do not interact with the electrons. That's why the constant weakens.
Sorry, why are there many different lines at the
I'm comparing with some previous ones. So my results are in this magenta band. These are some previous.
no, in the left part, there are many lines.
So these are coming from the Big Bang nucleosynthesis constants, and the Scobell line is CMB spectral constant, and Pixie is like a proposed. So this can actually strengthen this constant by time.
That's 4 cost.
4 cost.
And 26 MeV.
So I inject a photon around 26 MeV.
Okay.
And this is just about the photo dissociation threshold of the.
What does FEM mean?
So in this calculation, I have assumed that 100% of energy goes into the particles. Some neutrino or something that is really low.
Why can't give me a load constraint and give me a polar change?
We have to do with some cascading, solving the cascade. So model is inverted.
Model is
So they also probably do not solve the cascade numerically. So they do some analytical merging. And this is very close to this dissociation threshold. So that's why it's very sensitive to how you are solving the equation. That's why there is no difference. to go to like 100 MeV or GeV, probably the difference will not.
Or is there a band in your thing?
No, because
Everyone has a band, right? Whereas, others, he used only upper line.
Why is band?
because I'm injecting energy at between 10 kPa. So up to this point, I only talked about electromagnetic energy injection, but very high energy neutrino can also produce spectral distortion. So if we inject neutrino at this very high energy, they can pair produce some background neutrino or anti-neutrino and produce quark and gluon pairs, which after decaying can produce electromagnetic particles. So they can have some distortion. So this I'm considering a dark matter decay model to monochromatic neutrino and anti-neutrino. And these different curves are showing different neutrino energies. And this dashed line, I'm showing the CMB anisotropy constant from Planck. So the CMB anisotropy only cares about the gravitational effect of this radiation energy density. So it only cares about the total energy in the neutrino, and it does not care about the energy of each neutrino particles. So it is therefore more model independent. So our calculation is more model dependent. So I consider one case, but in this particular model, I get constant, which is like 3 or 4 order magnitude stronger.
Sorry, what is the process you said? Neutrino does what?
So if you have very high energy neutrino injection, it can pair produce some background.
They produce on background.
So we can
New static. Mediated by Z.
yes. So I use results from BQ, which is the
And goes to what? Z to QQ bar.
yeah. So at the end of the day, you will have some electrical
Or what, right?
first, but they will decay always.
But extremely low cross section, right?
Probably I just only care about the end product after the.
Yeah, but it's a very low cross section given by people.
But the lifetime is very small compared to the cosmological times.
Which like the decaying time. No, I'm saying the cross section is very small. After you decay, the neutrino has to interact with something, right? That cross section is extremely tiny.
So after pair produce, you have to make ions, quarks and gluons, which can.
No, you decay dm to nu bar, but nu then has to interact with something in order to leave its imprint.
But at very high redshift, the number density is also very high.
But still, the cross section is extremely tiny.
So I solved the equation, but it seems that.
So you should find a very tiny effect. Is this effect tiny? I don't have any feel for the y-axis. What is that?
So N effective is basically the neutrino energy base.
Yes, but that doesn't look very tiny. It's order 1 or something.
It's 10 to the 1.
Yeah, some 0.3, 0.4 something.
Yeah.
It is a large effect. How now? Why, in spite of this very small cross section, do you find a substantial effect is possible? You do agree it's a very tiny cross section, right?
Yeah, I don't remember, but I solved the. Oh, no, wait, that's the question.
What is this 10 GeV?
So the individual neutrino energy is 10 GeV. I mean, so basically what I'm saying is this is not being constrained by CMB spectral distortion because the CMB
What's the
system.
cross section? Sorry to interrupt. So just DM goes to during bar, right? So.
No, the neutrino then has to interact with another background neutrino, it says, via Z exchange. And what is the energy of it?
These are like 10 to the 4, 6.
Oh, so they are pretty high energy. Okay, that might be the reason why you find a substantial cross section. It's a very heavy dark matter, like a film or something.
So that's why it is a very.
That's how you pick the small level. Like,
It also depends on where you are producing. These are produced at which.
Yeah, like this red shift is like 10 to the 5, 6. That's what.
So this is energy scale. What is the temperature of the?
10 to 100 UV.
It's a hadronic system. Means all the nucleus.
Yes.
You have not considered any interactions with the nucleus.
Yeah, we talk about some of my work on semi-spectral distortion post-recombination universe. So in previous slide, I showed that these galaxy clusters can create spectral distortion, assuming these electrons having a thermal distribution, thermal or Maxwell-Boltzmann distribution, but they can have a component which can be relativist. So we did that. I'm trying to constrain this abundance of these non-thermal electrons. So what I did is basically I stacked about 1500 Planck identified galaxy clusters. So this is the stacked mapped at different frequencies. And so the thermal and relativistic electron population will have different signature across frequencies. So therefore, combining this frequency map, we can distinguish between thermal and non-thermal electrons.
What is the physics you're talking about? Gravitational flux. What are the like formation of galaxies?
So galaxy clusters are formed.
Yeah.
But, people often assume that the electrons are formed, but there can be a subdominant component where the electrons can be relativistic. So I want to constrain that is the abundance of this.
You take a homogeneous cloud and then you which undergoes gravitational collapse.
So the data is already there. I would actually. So this is what is,
Whatever initial inhomogeneities are there, you just collapse the thing, and then you're asking what are you asking for the electron spectrum?
so
Whether it is non-thermal,
relativistic.
it should be related to the inhomogeneity that is already present, or what?
There can be some particle acceleration processes.
Oh.
Magnetic field can accelerate.
That kind of.
And the spectral distortion signature will have different frequencies. That's why combining different masses you can.
So what are all the physics you put in? The physics due to magnetic fields and things like that, is that?
I just parameterize the non-thermal electron by power law.
And you don't care about what produced them, you just want to look at the effect of that.
First you want to see whether non-thermal electrons exist or not. And then you keep it for other people to see.
Yeah,
No, you assume a certain non-thermal energy.
I want to constrain.
Yeah.
You want to consider, so you assume some non-thermal. Okay.
And I want to just constrain this y parameter, which is related.
Yeah.
So the present data, there seems to be no signature of this non-thermal. And these three lines are for basically assuming different electron population. So this y and t basically like a number density of non-thermal electrons. So at present there is no signature, but with more number of clusters, like so this was about 1000 clusters, but with next generation experiment you can do like 10,000 kind of clusters. And
what is the y-axis here?
This is like a posterior, so this is like a probability.
Okay, what am I supposed to put?
So basically, where it is like 90% confidence.
Okay.
Totally.
So low y and t, what does it say? Like,
so these are basically allowed.
there's no detection, right? So below that black line is allowed. I don't know how to read this process.
Yeah, so basically with 90% of confidence, like this high value are excluded, but this y value.
Okay. And what is the scheme in 1, 10, 100?
Different electron spectrum.
10 means higher
Electron.
electron.
Therefore, the photons will be scattered at very high frequency. So it will be more than single and sometimes.
You check with the field of like 10,000 clusters or more, but the incidence observation, given certain fiducial value, must be constraining fiducial.
So the error bar will go like square root.
I understand. So what are the forecasts, for example?
Not done the forecast, I will just assume the error bar will go down. So that's why you have stronger constraint on y and t.
But this is the present data.
Yeah, so I will now move on to 21 centimeter distortion. So the 21 centimeter line arises from transition between the hyperfine state of ground state hydrogen. So this N0 and N1 are the electron population in these two states, and these two are related by a spin temperature called Ts. So basically you have the CMB spectrum. This is passing through a block of neutral hydrogen, and some of these photons will get absorbed at 1.4 GHz, which is the rest frame energy. And this need in this plot I'm just showing absorption, but it can also be emission depending upon the population in N1 or N0. So if the neutral hydrogen was not present, you have a Planck spectrum. So you know what should be the intensity if the neutral hydrogen is not present, and you measure this intensity. So therefore, the difference of the distortion is an observable of neutral hydrogen abundance. So this delta TB is the what is called the distortion, and it is proportional to the spin temperature minus TR radiation temperature. So in standard cosmology, we know the existence of CMB, so therefore it is typically assumed that TR is equal to TCMB. But we can have extra component like non-thermal, some extra radio background, etc. And this physics happens in the rest frame of neutral hydrogen. So one has to redshift it to our observation frequency. So that's why there is an extra factor of redshift. So this plot shows the expected distortion in standard model of cosmology. So in the y-axis, I have the brightness, and in the x-axis, I have the frequency. But because it is a line emission, the frequency is related to redshift by this expression. So lower frequency corresponds to higher redshift. So at very high redshift, the CMB and matter temperature are basically coupled. The spin temperature is roughly given by the matter temperature. Because they are same, so there is no distortion. But once they decouple, because the matter temperature is older compared to CMB, so that's why you see the signature in absorption. And after reionization, the matter temperature is higher compared to CMB, so that's why you see this in emission. And once the reionization happens, so basically you don't have any neutral hydrogen. There is no extra no signal.
Sorry, for emission, it is wherever that gas is present, right? That is that. For absorption, it is really the background, which is there is some background source which gets absorbed, right, by some intervening gas. And
Yes,
so it is
because
not
the
clear
matter
what is the redshift. I mean, there is some matching that has to be done. Doesn't. What is the redshift now? Is it the
So this
emitter
will
or
be-
the absorber? Or?
So this will be roughly around redshift 20. But before that is basically matter is colder than the CMB. So that's why there is absorption.
No, I guess maybe I'll ask you later. Yeah, it's more.
So I will consider a case where we consider an extra radio background on top of CMB. So this was motivated by this tentative signal reported by Edge's collaboration. So they measured this distortion of around 500 millikelvin, which is in absorption at redshift 18. But for a typical standard cosmology case, it is expected to be around 100 millikelvin. So the absorption depth was like factor of 3 higher. So therefore, people consider an extra radio background. So basically, the delta T functional formula is given by this equation. So if I increase the TR, so I boost this factor. So therefore, my delta TV increases. And it has an implicit assumption that this radio background does not affect the TS. Otherwise, the ratio will again be same. So that doesn't work. And I should mention that this measurement could not be reproduced by Saros. So in this talk, I'm just using it as like a reference point, but it's not important for this.
It was 95% cooled out, right? So in Saras, it was 95% cooled.
So this is the only positive detection.
It's not confirmed.
It is, yeah, that is the only, no other experiment.
We are trying to. So in this calculation, what they assume that this radio photons are low frequency photons, they just redshift. They do not interact with electrons. But these photons can be absorbed by these free electrons due to Webster law. So I am showing the optical depth of these photons. So these different lines are for different frequencies. And in the x-axis, we have redshift. So at very high redshift, because the universe is both dense and ionized, this optical depth is much higher. But once the recombination happens, then because there is very less free electrons, the optical depth is very small. But it's still a frequency dependent. So for some low frequency, optical depth can still have the outer point. Therefore, this heating effect has to be taken into account. And this heating basically affects this TS in this formula.
So if optical depth is small, that means absorption is more efficient.
No, depth is still. Optical depth is higher, means the scattering.
They travel longer.
Person.
Optical depth small means they travel longer.
No, other way.
So you tell me, let him tell, what optical depth small means,
Almost the free stream, so there is no trigger.
they travel longer.
Yeah, I observed is equal to I source either A bar minus tau.
That tau is the optical tau. Okay.
So we solved so basically to compute the modified 21 centimeter signal, we had to solve a Coppel's equation of so Nx is basically the injected photon spectrum, Tm is matter temperature, and Xc is the ionization fraction. You have to, and they're coupled, so you have to solve this equation. And simultaneously you solve the spin temperature and 21 centimeter distortion.
Is someone monitoring it?
You can go ahead.
Sorry, I just missed this part. Am I audible?
Yeah.
So just if you go back 2 slides, please. Yeah, so I see that like if there is an additional radio background which really is present at that redshift of Z equals 18. So what kind of like astrophysical or exotic sources do you think could produce it like strongly enough without violating like existing radio background constraints at very low redshifts?
There can be a population of radio galaxies.
Okay.
There's also some exotic sources like dark matter decay and etc. that people study.
Okay, thanks.
Just cross that.
Yeah, so inject a like a power law radio photon spectrum, and this plot is for a given amplitude. So if you change this amplitude, the curves will change, but the qualitative picture will remain the same. So there are a lot of lines, so I will explain. So here in the black we see the standard case. So this is the PCMB, this is the matter temperature, and this dashed black line is the spin temperature. So once you inject the radio photons, so this TR is boosted by a huge factor. If I don't take into account these heating effects, this matter curve is still here, and this blue dashed line is the spin temperature. And once I take into account these heating effects, the matter temperature is boosted from this line to this red dotted line, and this dashed red line is my spin temperature. So the difference between this line to red dashed and the same line to this red blue line, basically the difference that we create due to this heating effect.
So the spin temperature is the temperature of the
Okay. Not exactly. You have to also do different processes. In this plot, I am showing the delta TV, which is the observable for the same case. So this green point is the tentative edge detection. The black line is the standard cosmology case, and this blue line is without taking this heating into effect, and the red line is taking this heating into effect. So there is a huge difference when you take this heating into effect.
So I missed, like what is it that you're doing here? So how is the
So
you have the standard case, and what do you do about that?
standard case means you have the same photons from black background.
Yeah.
But on top of that, we add an extra radio background. So
And a radio background, which means what, that you have some frequency dependent flux which you add.
radio photons. So okay. So what people assume that means radio photons just red sheet. They do not interact with the electrons. Okay. So once you take this interaction into account, okay, that changes the behavior prediction qualitative by huge factor.
I see. And so what is which one is the one without taking into account
It's
the,
blue dash line, and this is also scaled by 1/3.
so the point is without taking into account, it looks like you can explain the data, but if you take into account this effect, then it goes away. Is that the point?
Yes.
Okay.
The radio photons, the generation of them, and at what epoch they were generated, you said that at any source. Does it effect on this particular dot, or they just have to be in the radio frequency at redshift level? That's the
Yes.
only.
And these don't thermalize with the CM.
Time scale is,
Different.
and this also affects this 21 centimeter anisotropy or spatial fluctuation, because in anisotropy we are basically interested in temperature contrast. So basically we have a hot object in front of a cold background or vice versa. And if we make the background colder, then this temperature contrast will also increase. So that's why this temperature anisotropy also has to take dissipate into account. Otherwise you will get some bias test. So now I will come to the last part of talk, which is the fast radical cosmological probes. So I'll just remind you that this, so I'll use the fast radicals to constant this Hubble constant at present day. I'll remind you that this Hubble constant is related to the age of the universe. And there are different measurements or inferences from indirect inference from cosmological data regarding H0. So so this plot basically shows you some of them. So in the top panel, you see this early or CMB measurement from this lambda city. And this these one are from some astrophysical books like supernova, etc. And there is some mismatch. So in the right hand side, I'm just explaining this fact a bit better. So from CMB, basically we measure this acoustic scale, but this acoustic scale is basically measured in angular scale. Acoustic scale is measured in angle scale, and one has to transform this angle scale into a physical distance scale. So that's why one has to assume some kind of model. So let's say lambda city model. After this assumption, one gets an estimate of H0, which is of the order of 67. And one can also use supernova at redshift less than 1 to measure this H0. So basically, you measure the redshift, but you do not know the luminosity. So for that, one has to do a technical step, basically, what means by calibrating to Cepheid variable. So all the technicality aside, basically this step basically gives you the luminosity of the supernova. So once you know the luminosity and the measured flux, you can get the distance. Knowing the distance and redshift, you can get an estimate of H0. And these two are very precise measurements, but these two are like separate from each other by at least factor of 4 sigma.
So the graph on the left hand side, all the late measurements are also probabilities.
No, not
Not all.
all of them. SUS is the supernova, but
I
there
see.
are other.
Both the others are all not.
There
What
are
is the-
some recent measured log number and the.
I think on gravitational wave measurements, the constant is not as strong because you have one bright side. But with 50 of them, one can get to this kind of this.
That would be radio galaxy, right? Will it come?
That is probably strong lens.
So what is that red line, this kind of in agreement line?
Show that too.
That one, so which one?
This is it the carbon that is the wind impedance?
Probably,
Yeah. So they do not.
that also keep on
use variables, but they do not use supernova. As soon as you remove supernova, it tends to come to 70 or a little below 70.
What do they use instead of supernova?
They have a particular standard kind of, they're saying carbon stars or something.
It's a recent.
It is the last 4-5 years they are coming. Okay, and they are actually having competitive constants with respect to the supernova.
This plot is 2019.
Yes.
Yeah, this keep on changing.
And they have new.
Yeah. So
Okay.
last year there in the Royal Society meeting, when we said on both
Okay.
okay, and there was a talk by the different which is very.
How do you know who's right?
So as of now, since wind impedance does not take the supernova into account, we only know that supernova is lacking this thing to the higher, but people have independently checked their analysis, reasonable analysis, they didn't find any systematic effect as such as well. So both results seems to be in agreement with all the cosmology that are not the assumption, so it's the astrophysics actually. So all the things that we know have been applied here, including the systematic uncertainties to the extent.
Supernova will be classified.
But they disagree.
So of course, red is right because they agree with CLT.
I mean, this number keeps on changing, so right now JW is still data to
Which number keeps changing?
this CCHP, this rate.
Oh, I see. It has changed since last year.
JWSP measurement, so it has shifted to probably.
Just calling it 70 is good enough. That's a fantastic achievement.
So it has shifted up now.
Yeah, this.
It's the error part, but the it is a relief that was by
Yeah, but it's really good.
this time.
Yeah, so that's why the point is basically using this fast rate burst to see if we can measure actually. These fast radio bursts are like millisecond duration transient, so basically you see them in a radio experiment for like millisecond, like a burst at typically gigahertz frequency. And their formation, how they are formed or what is the mechanism is not known. So they can be repeating, non-repeating, but in this talk, I only just care about an observable which is called dispersion measure for different frequency, light of different frequency travel reaches at different times. So I only consider this dispersion measure, consider this observable in this talk. And this DM is proportional to the line of sight integral of electron density. So DM is a major quantity, and this at present the FRP sample are basically redshift below 1. So we know we have an idea of what is the average electron density is. So basically I know DM and ME. So from that I get an estimate of the distance to this FRP.
So what object is like the favorite thing for FRP? What are they?
So this team object can have many components. So we are interested in this IGM or cosmological component, but there can be contribution from our own galaxies and also from host galaxies. One has to separate one from the other. So in this plot, I'm showing a sample of 100 FRPs with known redshift. So these are in these dotted points. And the red solid one is the expected TM assuming a homogeneous universe. But the universe is not homogeneous. So the electron density has scatters around the different line of sight. So this scatter is shown in this gray band. And one cannot compute this scatter analytically. So one has therefore to refer to cosmological simulations. So we have used some result from some cosmological simulation to get this scatter. So basically, therefore this TM provide this noisy estimate because this we don't know the exact idea of electron density in this equation. So NE is basically a bit noisy. So therefore we get a noisy estimate of electron.
Which contributes the most to those scatter. So
Cosmological.
So sorry, these are all models or are they constrained by observation?
These are data.
no, but the model, lots of model goes up, right? Like OIMW is the model of ISM.
Nice.
Actually, if you try any 2001, because in some direction, any
So NE is a black hole. There are two.
Okay, that is something else, right?
This is the fiducial one, which were used in 2001.
Okay,
But this blue one is where.
So this is one.
okay, that is interesting.
But this is model plus constraints from data.
Yeah, and
together
it's whenever I'm seeing, because now everyone is doing something. So let's go the earlier slide. So see, in say your host galaxy is like a Milky Way like galaxy, right? And we know in our Milky Way, the what is called DM host is like DM distribution like Milky Way, right? But in say Milky Way, the DM distribution is so different, ISM distribution, right? Depending upon which direction you are looking. But similarly, say you have the host galaxy, if your FRB is at the back side of the host or front side of the host, that can give almost say within our galaxy, we know DM maximum can be up to maximum can be 3,300.
That's why I
They are
picked DM host. Why I'm not assuming DM host. So I will extra DM host from the data.
no, but how? Yeah, so that the a problem, right? Because we will, it will be error by 300, right?
So I assume that DM host is given by log normal distribution and fit.
Okay, so that, okay.
That's a modeling assumption.
Yeah,
But I think the best thing is to model everything and fit together instead of subtracting it from the data.
Because there is 100 FRBs, the data is not constant.
Oh,
Once you have
this is so that is the best you can do.
Yeah, so like, now, 500,
localized.
okay. It is not time for finding the 100 every day,
But they're non-localized.
okay.
They,
Oh,
they cannot be reset.
And you need localized because
oh, because of cost.
So basically, for H0, you need the distance and this.
so you mean to measure Z, you need the localized.
To area.
I don't know where they are.
The great actually refinements, if you can identify a galaxy, so you know from other measurement Z of that galaxy, you say this is Z of that.
So the FRB itself doesn't have any characteristic thing which can help you get the Z direct, like a peak of the distribution or something.
It's just an incident duration strong first.
No feature with the peak in.
No, because for redshift you need,
No, if I have like a standard peak place, then I can measure Z by just how much is in this place. Right?
yeah, but peak means displacement from where things. FRBs are just different FRBs are just you momentarily get a pattern.
Yeah. So to this data, I basically hit H0 and the host galaxy component. So for this plot, I marginalized over this. So this is my constant over H, assuming like two simulations. So this simulation basically give you this noise for
What are the industries and go down?
like a cosmological simulation, which gives you this width. So that is the theoretical. So with the present data, we cannot distinguish between the H0 from supernova and CMB, but like few hundred to thousand probably position to distinguish.
Sorry, thing that Sanatan asked before. So intrinsic luminosity, how do you get that? Maybe you said it one.
So there are like three steps. So we have to locate the secret variable to a galaxy. Okay. So we measure the flux of the secret variable.
Okay.
So the secret variable has a characteristic that
Yeah, Cepheid is a standard candle, so I know
I know that intrinsic luminosity from there.
But the FRB,
Except for supernova. For FRB, I do not know secret variable.
sorry, here we need to know the intrinsic luminosity of FRB or no?
No, just the distance. So
Just
the
the
distance gives the distance. The supernova case, I need the luminosity.
Okay. I need to know the redshift and the distance. Okay.
And one can also use this information about this host galaxies to get some idea about the positive. So in the black line, I'm plotting the CDF of the inferred host contribution. And for this different line, basically what I took is basically I took the catalog of galactic pulsars and I plotted the DM as a function of the spin down range. So imagining that the spin down range is a proxy of the stellar range. So from this plot, it seems that like younger progenitors seems to be more prevalent for FRB. So from the distribution, I sample 100 FRBs for different scatter. One cannot
That distribution, the theory distribution seems much sharper, no?
because I have
series
a log number, so that's
Yeah. Yeah, that's. You can, normal you can hide many things.
one can also try to check if the DM host is pairing with redshift. So we parameterize DM host as DM host 0 and some power law kind of and I want to constant this alpha. So at present with the present data, alpha 0 or non-varying DM is still consistent, but the error bar is still very high. So this was my all the research that I've done. So my future research plan is basically this galaxy cluster cosmology. So basically from CMB maps, we can get like number of galaxy cluster as a function of redshift. And Ajay explained that this is actually a function of dark matter halo. So dark matter halo creates the potential wave, and the variance fall into that and form this galaxy. So therefore the number of galaxy cluster can say something about the particle properties of that. That encodes this cosmological information. And with present or upcoming CMB experiment, one can go to redshift as high as 2. So one can also do some astrophysics with these clusters. So like that.
CMB part.
Science of
CMB part.
not it.
It's useful for the clusters, of course, but I think that you will get more clusters by ground based because those are more deep. We have a blue sky, but
So that will then to include the arrangement. Yes.
Can also study like this annihilating or decaying dark matter in 21 centimeter maps. So these energetic particles will have some features at scale corresponding to the mean free path of these energetic particles. So from 21 centimeter anisotropy, you can study or construct these kind of models. One can also do some astrophysics like radio galaxies or properties of some early galaxies from this. And for FRB as cosmological probe, so in the current work, I assume that the expansion is given by lambda CDM model. We do not need to assume that. So you can be as agnostic as possible with a larger data set and check if there is some deviation from lambda CDM. And we can cross correlate this FRB with CMB. So basically, FRB gives me DL, which is proportional to electron density. And from CMB maps, we get a combination of electron density times temperature, which is called thermal signature effect, or electron density times velocity of variance, which is called kinetic signature effect. So combining these two, one can also probe some gas physics parameters. So that is.
idea about the scale as the 21 centimeter probe. How does your constraint, how will your constraint improve? Any focus that you have done, which the ones that you have done, that you can put the constraint here.
Basically, for which
Keeping that.
I'm not on that.
And are you planning to give constraints on radio galaxies that have redshift?
Yeah, one has to basically do all that. One has to do a simulation. There are some public simulations. One has to understand that because it is bit dense. So I'm planning to.
And these radio galaxies, are there models also?
You just put them inside the dark matter halo. Choose any number.
And how do you know that distribution? How many of them are there?
You assume something, you can compare it through data and check the matches.
Can you give more fundamental prediction? How? When at what redshift they are formed?
Yeah, because this 21 centimeter is a line map, so it is tomographic. So you can do multiple.
You can tell when they are formed and how their distribution is.
Yes. How many FRB do you think if you have 500 less FRB that would be the third one? You need FRBs with clear localization.
For H node, that will come.
So I'm missing something basic. So in that FRB thing, you say you can do this without knowing the intrinsic. So how can you say one more time? How
No, but it's not, I need a, so it's not a special transformation between distance and redshift. So the velocity, distance and redshift. Right? So it doesn't matter where you get the distance, for FRP, the DM gives a estimate, knowledge estimate of distance.
So if you have distance and redshift, distance is what distance? Luminosity distance.
No. See, you don't measure luminosity at all. Yeah, you have that integration, right? So it's to observe any radio signal. That's because see, radio wave is traveling in loop velocity, right? So there is a bandwidth. So lower part taking longer time, higher part taking shorter time. So it is getting dispersed, right? So if you give some DMX value of something which will straighten, correct for this bad separation. So he knows DM. And that DM is integration 0 to distance, electron density, any DM. So with from the you know any, so you get distance. So,
So if you have the DM, then you're saying you can infer a distance.
yes.
Okay.
So you
That's exactly what he's doing. That's his.
So
Knowing the redshift, you can.
yeah, and that is why there are thousands of different ways, but he can use only 100, where we know its galaxy they are coming, and from
So
the
that
galaxy we know that they we know the redshift from other observation. So DM of the FRP and
DM also would be dependent on which direction, right? So for that, you need to know the direction.
That's
Yes.
what he was saying also. Whether it's behind the galaxy or in front of the galaxy, any DM will be different.
And not only that, I mean, DM is a function of angle and all, right?
yeah, can you go there? Your that DM different components. Exactly. So see, like we pulsar people,
Yeah.
what we do, our DM, we have only DM ISM. So there, our DM is only the ISM in Milky, right? So in this direction, our galaxy electron density is more. This direction is low. So in our galaxy, we know the electron density map very well. So it means this only inside the integration any that is a function of theta longitude latitude. So that also we know, right? Which direction your telescope. So that goes in. And that host galaxy and an assumption that we usually take say 100 is coming from there, and IGN is taking as a dilute.
How much? I mean, isotope.
As admittedly, usually dilute, but as it is
What
very
is DM halo?
dark matter hello contribution to because they are also electromagnetic radio wave is getting.
By DM. What is halo? Halo.
Yeah. The DM is not dark matter.
But halo is dark matter.
Yeah. So DM due to DM.
Yeah, but DM does no dispersion. Dark matter, how does it do?
No, so this is like a dilute electron.
There is an electron in the halo.
Yeah.
Is there an electron, dilute electron density in the halo?
Surrounding our galaxy.
There is. How?
So in the X-ray,
Meaning hydrogen.
No. Something you need iron. Usually in our ISM.
Yeah, it might be
Free
ionized, but it is
electrons in, ionized. You
Okay.
can have free electrons in the halo during ionized.
I see. Okay.
Even outside, I get.
Yeah, so inside our galaxy, it's all goes to
Got
ISM. So
Yeah.
it's ISM. Hello is means when you have dark matter and everything, that's some free electron also, right?
And if you can interpret that plot that you showed for FRB results, which one?
Next one.
What is this saying now? So the
So
red
the-
one is your result of it.
So basically this band or scatter is basically like a knowledge of
Okay.
this estimate. And this depend upon cosmological simulations. This one.
Okay.
So these two cosmological simulations. So these are two cosmological simulations.
That one, yeah, it was from the same paper. It's your this paper, the
Yes.
earlier plot.
Yes.
So that peak of that red one is your best value for H, is it?
Yes.
Which is how much?
0.66 or
0.66. explains what? That
And
you
here
agree with
the-
the CLB value?
Yeah, it is consistent with both.
CLB value is 67.5 plus.
But central value is like, central value is at.
See, 74, 67, both are doing.
Yeah.
No, but the peak is at
So give him
the.
500, give him 500 of this and then you will.
No, no, the peak
Whether
is
it
at
is
the,
67 or 74.
peak is at the end. And the
Peak
width
is
is
at the
broad
early
enough that you
years,
cannot,
correct.
width is broad enough that you cannot say anything.
And is that the 1 sigma? What is the width you're showing? 1 sigma.
Yes.
Then it's not significant.
Yeah, another 8 years, and so it's getting time start.
More questions? What the decaying dark matter going to engineer? Does it affect the HL measurement? RG measurement? Because you are changing the energy density in the various number.
Yeah, so. So if you inject like very low energy neutrino, so there will be no spectral distortion signature. That will everything goes into radiation energy density. So basically scale effective parameter, and this scale effective parameter actually degenerate with H2. So by changing neutrino intensity, you can actually change it.
So you are basically enhance the HU
And you can by changing this because there is a degeneration.
and what is the maximum flexion you can allow without destroy and without changing the step maximum apex score.
So these
And there is a cost for different apex. Yeah, I'll go for. Yeah.
yeah, probably this 10 to the minus 8 is already low. So I have taken a larger experiment to show the difference.
Anybody in the room? If you. Thanks.
I see.